Welcome everyone. This is not a big class, but I promise it's gonna be like it will bring you to the frontier of graph algorithms actually. Yeah. Okay. So let me tell you about like what is this class about, what you would expect, right? So first of all, it's about graph. And graphs are basically kind of just, I'm not sure, like, yeah, it's really important, it's kind of everywhere. Every area of science just basically use graph to model it, to model anything that they care about. Because when you have objects and you want to model relationship between objects, the most natural thing to do is to use graph. Okay? So, it can be like a social network, or road network, shipping network, internet, knowledge graph, or something in biology like brains. Brains, you use like a graph to model it too, sometimes hypergraph. And one of the key questions that people care about graph is to measure how things are well connected. For example, if you have two places from A to B, how A is well connected to B. Okay. So when you talk about how, like when you talk about two things like A and B, you talk about paths in the graph basically. Like imagine that you have a graph B, and then you have two nodes S and T. Okay. Two nodes or two vertices. Okay. There are several problems that you might ask, like how well connected S and T are. And by well connected, it's not clear what you mean. It can mean many things. Okay. One thing is like maybe you can go from S to T really quickly, cheaply. So that is shortest path problem. Like, can you find a way to go from S to T instead of many hops like this? Many hops. Maybe just go this way. That's the best way. Okay. So that's like to find cheap path. Okay. But another way to measure how well connected S and T is you can ask like, can you find many disjoint paths from S to T? So that also measure how well connected S and T is. That corresponds to max flow problem. So, okay. I wonder like how many of you have seen algorithm for solving shortest path before? Kind of? Okay. How many of you knows what is maximum flow problem? Okay. So, okay. And for the one who have seen what is maximum flow problem, do you know how to solve it? Like, have you seen algorithm for solving it? Can you raise your hand if you have seen? Okay, some, okay. Like half of class. Okay, good. So, okay. So maximum flow is basically, like right now, if you haven't seen it, it's basically like the problem of trying to find many disjoint paths from S to T. Right? That's the problem. Okay. And another way to ask is, can you find, instead of just many paths, you want to ask, you want to find many cheap paths. Okay. So for example, if like S and T has basically so many paths here, but they are all super long. Like let's say They are like 1,000 long. Yeah. But there are many. But you might have another set of paths here that are like just length 3. Maybe the better way, like you wanna find this set of paths instead. There are many of them, not too many, not as many here, but it's cheaper. Okay. So that would correspond to mean cost flow problem. And that is also another problem that kind of actually really important in graph algorithm. Okay. So in general, this is the question that you ask to find good structure where S and T can communicate well, whether it's cheap, like a cheap path, or many paths, or many cheap paths. People ask similar problem when you don't care about just one pair S and T. But what if you have many pairs S and T? Imagine that you have S1, T1, S2, T2, and maybe S3 here, and T3 here. Okay. And one can ask similar question about connectivity between all pairs S and T, each pair S and T. You might want to find like cheap path that connects each pair, like S1 to T1, S2 to T2, S3 to T3. This should be cheap. All of them should be like short. Okay. And that corresponds to transshipment problem. It doesn't matter if you don't know the name of the question, the name of the problem. Okay. The point is that it's well studied. Okay. You can ask about many paths that connect all these pairs too, and many cheap paths. All of this corresponds to some version of multi-commodity flow problem. Okay. So this is like a question of finding good structure connecting every pair SITI.
I just want to interrupt you once. Will you be sharing the slides or should we take down notes?
It's good. Yeah, it's on the website.
Canvas?
Canvas. So let's see. So if you go to Canvas and go to File, and then the slides there.
Alright, thank you. Alright. I want to mention another thing. Instead of path, we talk about trees. So imagine that you have one node here, call it a root R. And we want to measure how well R, the root, is connected to the rest of the graph. So imagine you want to, instead of sending one message from S to T or going from S to T, you want to make, instead now you have one node R, and you want to broadcast information from one node to the rest. Okay. So you ask how well this one node is connected to the rest. And you can ask, okay, one way to ask this is to find cheap trees, the tree that connect from R to the rest in the cheapest way. So that's minimum spanning tree problem. If you want to find many disjoint trees that have R, that is a tree packing problem. Many cheap trees, that's a mean cost tree packing problem. So this is like a question that is about finding good structure from broadcasting information from R. So these are the example of graph question where like this cost is actually kept. Like we will try to attack or get really good algorithm for it in this course. There are other questions in graph like graph coloring, something else like
finding a clique or something else. Yeah, many things. There are many things that is not just this problem, but the question that I mentioned, you may have seen some of the questions that I mentioned before, and it really is kind of one cornerstone of graph algorithms. One key part of graph algorithm. So the question is kind of finding good paths or trees, the thing that I mentioned, or finding bad cuts. What do I mean by that? It means that if you know that you cannot achieve such a goal, like for example, if you cannot find many paths connecting ST, can you have some certificate that shows that is not impossible? That is just impossible. So what the certificate to say that such a path or tree, the set of paths or trees that you want does not exist, is usually is to return some cuts in the graph. Cut is like a set of vertices. Yeah. For example, if you have S here and T here, and if there exists some set here, some set of node S such that there exists only one edge crossing this set, if you ask, can there be two disjoint paths from S to T, then the answer is no, right? Because no matter what, S need to go, like the path from S to T need to go through this cut, and there is only one edge here. That's an example. Okay. But yeah, this high-level question basically encompasses like many central problems in graph algorithms, and like you will see that along the way, like to solve this question, you will develop some algorithm for graph clustering, like clustering problem, like finding social network, like cluster in social network or something like that, or graph compression, how to compress graph into something that you care about, and you see an example today too. And basically, what we want is to solve this set of problems by designing good algorithms. Okay. And what do I mean by good algorithms? Okay. Any of you have suggestion? What is a good algorithm? Yeah.
So efficient.
Efficient. It should be fast. What else?
Maybe not using too much space, like space efficient.
Space efficient. Time efficient. Space efficient. Yeah. Time efficient. Space efficient. What else?
Perhaps easily implemented.
Very good. Yeah. Easy to implement.
Deterministic.
Deterministic. Yeah. Randomized algorithms are just harder to debug, or it can make errors. Okay. Deterministic. What else?
Potentially good approximations.
If it is approximate, then it should have good guarantee on approximation. Okay. Any other ideas? Yeah, one thing that is quite important is that it should be correct too. Because many algorithms that people use is not actually correct, like heuristics. So we kind of want that too, right? Okay, fast, I agree. Potentially, it should be linear time. Near linear time, like polynomial time is kind of good, maybe in the past, I don't know. That's my opinion. Like near linear time, you need it.
like especially when the graph size nowadays is just billion nodes. It's just impossible without nonlinear time algorithm. Deterministic, yes. Parallel algorithm. Here is important too. This is like something that people in like Google would like. For example, you might have heard of MapReduce. That's like MapReduce model. People want to have an algorithm that kind of, if you have many computers, you can basically speed up the whole algorithm proportion to the number of computers that you have. Okay. So if the problem size is a million, and you have million computer, maybe you want this depth, the time, the parallel depth here to be like close to logarithmic, polylogarithmic. That would be good. It should be maybe the even better algorithm is distributed. If your data is kind of distributed across many computers, it should still be able to solve the whole thing. Maybe even when one computer doesn't even know the whole data of the input, it can still communicate quickly to each other and solve the whole thing. Dynamic. What do I mean? It means that suppose that you have the whole input, and then let's say one edge of your graph is changed. Maybe you insert one edge to the graph. You need to run the whole algorithm from scratch. You shouldn't. That's like we want to make it dynamic in this sense. So when the data change a bit, just update your data structure a bit, and then you can return the whole thing quickly. Simple to implement. Yeah. And importantly, it should be easy to understand too. Like people need to communicate. So we want this. What else? I'm not so sure. Yeah. Okay. And now, like, the thing is that the techniques that I want to tell you for the whole semester, which is called graph decomposition techniques, it seems to be like one of the powerful tools that help you designing good algorithms in this sense. In the sense that it gives you many times fast, deterministic, sometimes distributed, sometimes dynamic. It has been successful to give good algorithm in many of these dimensions. Okay. You might have seen Dijkstra. Dijkstra algorithm is fast. It's deterministic, is correct. Dijkstra is not parallel, not distributed, not dynamic. Okay, it's simple to implement and easy to understand. Okay. So, but can we get Dijkstra algorithm for solving shortest path that is also parallel, distributed, and dynamic? That's a good question. Okay. What about like something else, like minimum spanning trees or something else? We want all this. Yeah. Sometimes we cannot achieve all this simultaneously, but it's a goal that we want. We can pursue for it. And let me give you some highlight in like the last few years. This technique, graph decomposition technique, has been given some really nice result in the past few years. For example, Max-Flow problem. Yeah, Max-Flow is, I didn't define it yet, but it's one of the really cornerstone problem in graph algorithm. That is, you have an SRT, find many paths, many disjoint paths from SRT. Okay. People ask how to solve this for a long time. Like, we know how to solve it in polynomial time, but just last 2 years, basically, that's when we know how to solve it in near-linear, almost linear time. So throughout the whole course, I will use M for number of edges in the graph, and N is number of vertices. And this is basically almost linear time. It's m to the 1 plus little 1 in the exponent. Okay. And okay, there is a algorithm for solving global min cut problem. You have a graph. You ask how many edges you need to delete so that the graph is disconnected. Just to disconnect some pair from each other, from some pair of vertices from each other. It's been known how to solve this randomized 20 years ago or 30 years ago, but deterministic last year. Deterministic dynamic connectivity. It's just asking if S and T has some path to each other, but dynamic. You can delete and insert an edge. And it turns out that for each insertion and deletion, you just spend something like sub-polynomial time. So it's faster than any n to the, this is like small, right? This is like less than n to the 0.0001. Right? So this is quite fast. Distributed algorithm for listing triangle in the optimal time. Some parallel algorithm for min cost flow. This is recently that we did together with my student Yahweh here. So it has been really successful, and like the technique has advanced so much, especially in the last 10 years, which I have helped develop quite a bit. But the thing is that although this technique is so powerful, there's no good place to learn this. So it's not well understood by many people in the world, really. So my hope in this course is basically to give you this hammer, so that once you learn it, then you can use it to solve open problem in graph algorithms. And eventually, I hope that from this course, we will maybe together, you will write some script for each lecture. I will talk about this soon, and then I will compile this together, and hopefully, after revising many times, then it gives to the world a good textbook on these topics. Okay. So this course in a quick glance, we will care about path and tree problems that I mentioned. And this is when you talk about throughput, finding many paths in SCT, there are a set of problems that you care about throughput. I will not define this problem yet. But another set of problems is when you talk about distance to find shortest path, for example. And there are problems that you care about both distance and throughput. So these are kind of already cover so many problems in graph algorithm literature. And the techniques that we will develop is graph algorithm. Yeah. This is just for the quick glance of the whole thing. You don't need to kind of understand every word, right? I just kind of want to tell you quickly how this whole course is structured. So the techniques that we will try to tell you is graph decomposition. And for the distance-based problems, there has been development since the 80s called low diameter decomposition. There are hundreds of papers on this, and people use it to attack distance-based problems. There is a more recent one called expanded decomposition that is good for throughput problems. And there's a more recent one called length constraint expander decomposition that is kind of good for all of this. Okay. and like I'll try to like teach you all this thing basically. Okay. So basically like the graph decomposition here is like kind of versatile, unified tools that it's just useful for graph problem. Okay, so the key concept that you learn in this course, one is expanded decomposition. I will define it today. There will be another thing that maybe in next week I talk about this expanded balance separator. I tell you what it is. This is just some nice picture that I made sometime. And there are like some other objects. These are some like graph clustering objects. One you learn about it is like some quite natural graph clustering. And they have some relationship between them. And behind all this, there is a thing called cut matching game that if you want to implement this thing quickly, you need cut matching game. Again, yeah, doesn't matter what it is right now, just to tell you. And now, like this graph structure, the hierarchical decomposition of the graph will lead you to get some nice application in theory, like to specify the graph, to reduce the number of edges in this graph, and something else. And then this kind of class of objects that is cool will lead you to good algorithm that I mentioned in the beginning. Good algorithm for paths and trees. Okay, so this is like really quick kind of glance of the whole course, and like basically we will kind of go through like each of these boxes together. Okay. Right. Now a required background in this course. Since like my intention is to bring you to the frontier of graph algorithms, I will really need to assume something. Cannot just start from max flow. What it is. So you need to know like some basic graph, some basic algorithm like sorting, some basic data structure like queue, stack, that kind of union find, that basic thing. But also like some graph searching like breadth-first search, depth-first search that you need. Some shortest path algorithm like Dijkstra, Bell-Manford. That is something that sometimes I would just assume. But quite importantly, I need to assume that you know what is flow and cuts. You know Menger theorem, what is and max flow mean cut. If you don't know this, it's okay because I have some material that you can look up online, but I will ask you to look it up yourself. Also, basic probability, some concentration bound like Markov bound, union bound, Chernoff bound. Not like maybe you don't need to look this up right now, but whenever we start using randomized algorithm, these are the tools that we just kind of use it naturally, and then like if you feel that you didn't follow, try to catch up on this. But the point is that like anything that is in EECS 477, if you have seen material from this, it should be enough. If you haven't, then I actually have some YouTube video on this. So my recommendation is that if you haven't seen what is max flow, cut, what is Menger theorem, then like go to my website and see this. Look at the video about flow and cuts, and then learn it. Okay. Any questions up to this point?
what about this course? Okay. Okay, so let me talk about logistics quickly. Okay. Right. So, yeah, this is just some basic information. We have discussion. I recommend you to come to discussion session because sometimes I will just go through the topics that we discuss in class, but sometimes I will just teach new things. There's so many things I want to teach you. Yeah. But if you cannot, well, everything is recorded. So it's office hour on this day. And yeah, you can ask questions on Piazza. And if there is any feedback that you can email me on anything, but if you want it to be anonymous, just feel free to send me like any message through this form. Okay, and the grading of this course, there will be like 3 problem sets. Each of them worth 10%. There will be scribe notes. I will talk about it now. And research project, I will talk about it later. And at the end, there will be like some quick oral exam. This will be like kind of easygoing, but just to really kind of check that you understand the concept in class. So maybe like 15 minutes talking on Zoom. But if the key way to improve your understanding and develop intuition and get familiar with things here is to solve problem sets. So this is quite important here. Okay, let me talk quickly about scribe notes. As I said, that my goal here is to kind of make this techniques accessible to not just like 15 people, but much more than that. And so it's kind of important for us to work together to like to write this down to make it accessible to other people. And so basically, everyone will kind of need to scribe maybe 3 lectures. Each will constitute 10%. And you can book your slot on the spreadsheet in the link here. Okay, you can go to the website and maybe I just go here. Like there will be some. This is like basically the slots, and you can put your name here. And what? And then you can go to the overleaf project, which I already made. And like create some, like if you want to scribe the first lecture, then you make the folder here with the date here, and then you scribe. Yeah. So in the case that, let's see, like I try to finish everything on time, but if suppose that I didn't finish some small thing in time and start like the next 5 minutes or 10 minutes on this small thing to the next class, it should still be in the same scribe notes, just for continuity. And the thing you should write is like you should make it complete and should make a good start. You can have a look here, and if you can ask any question, if there's anything unclear, you can use AI to polish. I don't mind that, but you should understand what you wrote. Okay?
And the goal might be to finish the scribe within 10 days if you plan to scribe some lecture. But the deadline is not so strict. Okay. But once you are done, like you might want to like have a meeting with me quickly, just so that I can see what you did and ask you if you understand everything that you scribe. So this will help you to understand at least the concept from that course, from that class completely too. Okay. Okay. And if you have a look at the scribe of others, then if you find any typo, you can just edit it. If you find like some real issue, maybe email it to me. I might give you a bonus point. Okay. Okay, that's it.
I just want to ask, how detailed should this scribe be? Is it just what you speak in class, or is it?
So it should be basically every content in the class, the whole content, and like also need to include a proof. Sometimes I write a proof, like on slides. It's not quite like formal or super complete, but the goal is like you really understand it and complete the proof. Okay. And include some reference. And it would be even nicer if, like, I try to make many pictures in class. I put it on slides many times. Yeah, but if you have some other ideas, like how to make the illustration even better, then go for it. All right. Okay. So let's start. Okay. So from the quick glance of the whole course, you have seen the word expanders. We will deal with expander quite a lot in this course. But now, expander in TCS or theoretical computer science actually really has kind of two different regimes. So there's like, one is called, like, I call them tailor-made expander. This is like a really like a graph that is sparse and has really strong connectivity, although it's sparse. Like, okay, first of all, like, what is the most well-connected graph? A click, right? If you have n nodes, just connect all pairs to each other. This is the most well-connected graph in every sense. But can you get a graph that is sparse yet well-connected? That is what people usually like think of expanders. Expander is that thing. It's kind of contradictory, but it's possible. And tailor-made expander is like such a graph that is really sparse, yet it's really strong, has really strong expansion, well connectivity. Okay? And it's kind of hard to even construct it. There is another kind of expander that I call it expander in the wild. And it has weaker expansion guarantee, but you can find it everywhere. And this course is going to be about this thing, the second one. But let me tell you quickly what is the first one, just so that you know and like you expect, like you know about literature a bit. Okay? So the goal of expander in this first regime, the goal of researcher usually is about to construct this thing, to show that it exists and to show how to construct it deterministically and fast. And the key object is something like if you look up literature, something called Ramanujan expanders, lossless expander, monotone expanders, or more recently, high-dimensional expanders. Doesn't really matter what this is, like, but if you say this word, it's basically in this regime. It has many applications in coding, correcting code, coding theory, pseudo-randomness, PCP construction, and some sampling algorithm. But we will not really talk about this. It's something kind of, it's something else. But what we would talk about is these expanders in the Y, where basically the goal usually is about you have any arbitrary graph. You don't just tailor-made graph. You are given some crazy graph, any graph, and you want to find or use the expanding subset, expanding structure inside any graph. Okay? And the key objects that we will look at, and I would talk about a lot, is expanded decomposition and expanded hierarchies. We define this. This one today, the decomposition is today, and this is next week. And there are many applications of this just in graph theory and graph algorithm, and also dynamic data structure. Okay? So we'll talk about this thing. So this is just so that once you look up the internet and search for the word expanders, you know that there are kind of almost disjoint set of literature. Okay, let me start now with some basic definition. I will build up now go to a formal definition of what is expanders. Okay. And the first notation that we will work with is unknown weighting. Unknown weighting is basically A is a function that map vertices to some number, some negative number. So
Negative or?
non-negative,
Oh.
non-negative. And for example, think of A as the indicator vector of a set. Okay? So if I have a set of nodes S, A could be an indicator vector, meaning that here A of V is 1 if V is in S, and 0 if V is not in S. If it's the case here. Or the node weighting can be like a degree vector of the graph, which means that A of V is just degree of V for all V. Okay. So, and I will use this notation like A of S is just a sum of all nodes of the node weighting of every node in S. And the size of A is a sum over all nodes of A. So for example, like degree of S is just the sum of all degree of all vertices in S. Question about this? Alright. And now I can talk about expansion. So I would say that a node weighting A is phi expanding in G if the following is true. So think of G as a graph and it has capacity. Okay. Capacity here is it's just it assigns capacity to each edge. Assign some number to each edge. And A is phi expanding in G if for every cut, for every S, you have this. That is the total capacity for the cut. Like if you look at the graph and if you look at the cut S, the total capacity that cross S here is big. How big? It's at least the A, the size of A from both sides. Not from both sides, like maybe take like it's at least the minimum size, at least the smaller size of A times phi. So that's the definition. Okay. And I said that this set S is phi sparse cut with respect to A if this thing is false. If the cut is kind of small with respect to A. So if this cut is small with respect to A, then this is phi sparse cut. So just from this definition, it means that A is phi expanding in G if there is no phi sparse cut with respect to A. So let me give you some example. Suppose that A is like an indicator vector of this guy, of this set of nodes. Like I put number 1 on these nodes. Okay. Then if you look at this cut S, okay, then this cut S is going to be like 1/2 sparse. Actually a bit less than 1/2. Why? Because the size of A here is like 3. The size of A here is more than 3. So, but the cut size here is just 1. So the capacity crossing, let's say that this is the capacity of this edge is just 1. Okay. Usually I think of this capacity as unit capacity. So the capacity of every edge is just 1 for all edge. Usually when I don't specify, like I mean this. Maybe actually. I don't know how to turn off it. Maybe it's okay. Is everyone okay with the light? Okay. So is this example clear? This is a place where you need to make sure that you understand the definition. So, yeah. Basically you look at the cut and then you look at capacity of the cut over mean of the size of A on both sides. This is basically like the number 5 here. Okay. So this is like 1 here, and this is like 3. So basically this is like a 1/3 sparse cut. So the intuition is that if you can find a cut such that you can remove small number of small capacity of edges and separate A in the balanced way, then phi would be small. Okay. If phi very small phi sparse cut means that you just remove some small thing and you separate a lot of things. You look at the ratio, how you need to spend energy to remove things, to separate a lot of things from each other. So
Well, what would be the capacity in the example you said? Would it be 1?
just one.
Because there's one.
Just one edge
just one,
here.
yeah.
And if I say that A is phi expanding, and if you think of phi as something big, close to 1, then it means that no matter where you try to separate A from each other, you need to spend a lot of effort to separate it. That's the intuition to kind of have in mind. If it's expanding, it means that you need to, if you want to remove it, separate A in the balanced way, you delete a lot of edges, a lot of capacity. And I said that the graph G is a phi expander if the degree of G is phi expanding in G. Okay. All right. Can G be phi expander where phi is more than 1? Anyone? So actually maybe I should be more precise here. Maybe the degree of G for this node is basically like the total capacity of edges from like you look at all edges from B here, and you count the total capacity of all edges incident to B. That's the degree. So it's like capacitated degree. Yeah. That's what I mean. So I said that this is actually impossible. Why? Because if you take any cut G here, okay, if you take a graph and you take any cut, so now if this is phi expanded, it means that capacity from this to this is at least phi times mean of degree of S and degree B minus S. Okay. So what is degree of degree S? It basically kind of count all the capacity of edges incident to everything on the edge side. And degree of V minus S just count the total capacity of the guys on the other side, right? But what is this? This just count the capacity of the thing that cross this thing. But this, like, this is the capacity S, B, and S. But this is already counted in both of these things. Okay?
Also, and since phi is greater than 1, it cannot happen.
It cannot happen. Yeah. Like, this thing is obviously at most each of these things. So it cannot be the case that phi is more than 1. Yeah. Question about this? Okay. All right. Next question, can it be the case that let's say that S is the indicator vector of some set S? Can phi be more than 1? What do you think? Yes or no? Can phi be phi expanding and phi is more than 1? Who think no? Who think yes? Okay, why do you think so?
I think that if you have like a relatively like small set that has is well connected to everything in the other set, then that should produce a small like A of S, but it should have a very high capacity.
Good. Yeah, let's look at this example. let's say that the graph has two nodes. S and T. But let's say this edge, there are many edge, or actually even one edge. But the capacity here is 10 to the 10 or something huge. Right? Now, like, if you look at a cut, there is only one cut, which is this cut. But this cut, if you look at the ratio between capacity over S, that's okay. Let's say that A here is just 1 on every node. So this is like the node rating here is like it's just 1 here, let's say. Right. Then the capacity here is like 10 to the 10. But when you take the mean of A from both sides, this part is just 1. So this is much bigger than 1. Right.
So this is not a simple graph, isn't it?
This is not a simple graph, it's a graph with capacity. So, like, it has capacity. Yeah. You can have some. So by simple graph, you mean like it has just unit capacity? Is that what you mean?
I mean, there is only one edge between, possibly one edge between two vertices.
Yeah.
And no self loops.
Right. Yeah. Then this is simple, but it has capacity actually. But you could just even like try to build some example that, you know, let's say that it looks like this. Like, so it's just so well connected here, and the node weighting is just 0 everywhere except S and T. This is just still simple graph. For every pair there is only at most one edge, and the capacity is just 1. Then you can actually still say that A is much more than 1 extending in this graph. Yeah. So many times I'll like, most of the time we think of A as degree node weighting. Many times you think of A as degree node weighting, and that's why like once A is degree node weighting, like phi is at most 1. Okay. Good. So now, when I say expanding without phi, just so you know that I think of phi as something like close to constant, but not quite. By close to constant, I mean phi is at least 1 over polylog n. N is the number of nodes. That's what I think. So, yeah. So when I say something informal, just say expanding. That's what I mean. Okay. And if G has many connected components, like this graph, there are like components here, there, and there. When I say that A is expanding in G, what we really mean is that A, when you restrict yourself to A inside the component, you know what this means? It means just like, you know, A is, so yeah, A intersect U of V is just A of V if V is in U, and 0 otherwise. That's what I mean. This is just a notation. So when we said that A is phi expanding in G, if for each of the component, each connected component of G, A intersect U is expanding in G. So A is expanding in each of the component. And G is a phi expander if each of the component is a phi expander. Okay, let me give you some clues. Which one is an expander? Okay. Is a clique expander? Is this one an expander? Yes or no? Someone need to say. Someone need to speak.
Yes.
Okay, good. How about this one?
No.
Just a single vertex. It turns out that it actually is an expander by like a kind of trivial, like this is kind of corner case, but it is. Why is that? Because like there's only one cut here that contains the whole thing. But like by definition, like the cut S need to be not containing every, like, okay, this is the point. Here I only look at a set S such that it doesn't contain all nodes. Or like S need to be like, S here actually need to be such that it's not empty and it's not the whole thing. Okay? But if the graph has only one node, then like there is no such there is no cut basically. So that's why like a single vertex is just expander like by kind of stupid reason. Yeah. What about star?
Find one cut, so I think
Hmm?
you can find one cut, so I think it should be right.
You can find one cut such that what?
You can disjoint it from the other way.
So you said is it an expander or?
Yes.
Okay. Yeah. Well, it is an expander, yes. But to say that it is an expander, you need to say that for every cut, it is not sparse.
Okay.
Right? That's what it means. Like, to be expander, it just means there is no sparse cut.
Okay.
Okay, there is some cut to consider, but if no matter where you consider, let's say this cut, well, the cut that crosses it is like 3, but the node weighting on this side is also like 3. So no, like for every cut, you like it's kind of expand.
So we have to check every cut to see if it's
Yes.
Yeah. Are we talking about one expander, or I mean, if we make the 5 very small, then they might be expanded.
Yeah.
I mean, more likely. I mean.
So yeah, so that's what I mean. Like when I talk about expander, I mean like think of phi as 1 over polylog.
Oh yeah.
Yeah. And actually, in this case, like this star is something like, actually it's a 1 expander. So it's actually a strong expander. Okay. And hypercube, do you know what is hypercube? It's like you can draw the cube, and then you can make another dimension. Like this, and then like connect each of these in the correct way. I don't know. Yeah, connect it in the match them in the correct way. And once you make this, you can go to another, like double this again and so on. That's hypercube. And it turns out that hypercube is 1/log in expander actually. So it is an expander too. This is not easy to see, but like you kind of feel it from the picture that it kind of quite well connected. Okay? You cannot easily find like some cut that you cut a few things and it's separate in a big way. Okay. What about this thing? This joint clip. Is it an expander? Well, yes, because that's how we define it right now. Just say that each component is an expander. Okay. So each component here is an expander, so it is an expander.
It's kind of like the case we viewed before, where it's like many connected components.
Yeah. Look at each connected component, and each of them is an expander. Then we said that the whole thing is an expander. Empty graph. This is kind of another stupid case, but yeah, we define it to be expander because this is just each component is just single vertex, and a single vertex is a expander here. All right. How about a dumbbell like this? Is there a sparse cut here? There is a sparse cut, which is this guy. If you cut just one, it separates like half of the volume, half of the degree from each other. So that's like really efficient cut, very sparse cut. This is not an expander. What about a path? Yeah, same, right? Just cut once, separate half and half. So if there is like, basically, yeah, if you want to see, if you cannot find a sparse cut, that's an expander. Okay, now like, if you look at this graph, okay, so this is all expander. Let's look at the last one here. Okay. And then let's say that I define the graph to be somewhat complicated, but I just basically define the graph so that the degree on each node equals to A, exactly. For example, I start with a node weighting A, and let's say that I assign A to be like 2 here, 2 here, 1 here, and 1 here. And now I want to define a graph in such a way that the degree of this node is exactly 2, the degree of this node is exactly 1. How do I do that? I can just define the capacity for each edge to be exactly this. Okay. And if the capacity of every edge is exactly this, then you can see that the degree of the node V is just the sum over all node U. AU, AB over A of everything. But this is just AV times AU summing over all U is V. But this is just cancel to each other. So this is just AV. So the degree of every node V is just AV. So in picture you can, and this is an example, if I set 2, 2, 1, 1 here, then I just put the capacity of this edge should be like this thing, like multiply together over 6, and the degree, there is a self loop here too. 2 times 2 over 6, 2 times 1 over 6, 2 times 2 over 6 here. Okay. So everyone understand the definition of this graph? Question about how do I define this graph? Yeah.
Are there any positive graphs where it's like not known as an expander?
Good. The thing is that given any graph, we can actually approximate phi efficiently.
Okay.
So even if we don't know, we can compute it. Yeah. You will see, we will learn about this algorithm in next 2 weeks or something, or 4 weeks or something. Yeah.
In the sum over U, V is not in the sum.
This is sum over U.
Yeah, so V is not one.
Yeah, V is not one of them.
Yeah, so how does it cancel? How does it cancel with?
Oh, because this is a capital V, right? And this is sum over all nodes U. So this is basically sum this thing. This is capital V here. But this thing is just AV, the A of the whole thing. So this is just A of the whole vertex set, cancel with A of the whole vertex set.
Oh, I just saw like V, like the vertex V is not in the sum because it's not. Like I saw you're summing over its neighbor.
No, this is summing over all nodes U.
Oh.
Because like this node, every node has some edge to every other node. So like the neighbor of V is every node. Yeah.
Oh, there's a self loop. Oh,
There is a self loop too.
Oh, okay.
Yeah. Yeah, there is a self loop here. Yeah. Okay. So I hope you understand the definition of this graph. And you can see, and my claim is that yeah.
In the cap function, if UV are sets, so are we enumerating all the edges within those sets?
If U and V are set like U and V here,
Yeah.
then you look at all edges crossing the set, yeah, crossing the two set, and sum them up. Okay, but here this is just like two nodes here. Yeah. Okay. So this is an expander. This is an expander, and you can check this. And how you think of this is just basically it's a clique, but you try to scale, like it's just a clique, but you scale like capacity so that it is A. Yeah. You can check if you don't see that this is an expander. Okay. All right. Let's see more example. This is like a clique and a path here, long path here. Is A expanding? Like A is just like some set inside a clique.
It's not.
Why?
Because, I mean, you cannot, see, A is just the set, and within the set you cannot still find something like which will make it sparse, right?
So if you cannot make it sparse, if you cannot find sparse cut, it means that it's expander.
Okay. Yes, it is expand.
So it is an expander. Yeah. Yeah. So yeah. To say that it's expanded, it means that it's well connected.
Mm-hmm.
So yeah, true. Like A here is expanding in G. Because no matter what, if you want to separate A, you need to kind of separate the clique.
Mm-hmm.
You cannot separate clique in a sparse way.
Mm-hmm.
So A is expanding. G is not. You could just cut it like here. That would like cut G into the balance way, but it doesn't really separate A. So G is not expanding, X is not expander, but A is expanding. I hope to give you many examples so that you get this intuition. We need to work with this quite a lot. What about this? Let's say that this is like a set F, and let's say that maybe I should say that A is let's say I put A here to be 1, 1, 1, 1, 1, 1, 1 here. A is like this. A is just like 1 on each of the endpoint of this set of edges. Is it expanding? Why?
So you still have the one edge that you use to
Exactly. You can still cut this guy just once and separate many A from each other. Okay. What about this one? Let's say A is just 1 and 1 here. Is this A expanding? Yeah.
Yes, because like to kind of separate it, we'll have to like detangle a clique, which is. So
You could cut it here though. You don't need to cut through the clique.
Is that like one edge or one path?
This is just one edge.
Should be expanding because it's, you have capacity 1 on each side and you're cutting with, or you're cutting an edge with capacity 1.
Yeah.
Is 1.
Yeah. So okay. We don't cut through the clip but we can cut it through this thing. But the cost of this thing is 1. Okay, just need to cut once. But how much can we separate A from each other? It's just 1 here. It's not like a big mass of A. So this is like some cut, but it's not so sparse. It's just like 1 sparse. Right? The cuts here is capacity 1, but it separates just 1 from each other. So it's still expanding. So basically when the intuition here is also that if A is so small, like if there are not too many things to separate, then A can, like you cannot find like so very sparse cut. Okay.
So the difference between this example and that one on the page before this one is that the definition of A is different.
Yeah, exactly. In the dumbbell here, when we talk about expander, it means that A is a degree not weighting. So it's about A is a whole thing, it's a whole graph. Here we cut once, you separate a lot. Now A is like just here. So we cut it here, we just separate this node and this node together. Just one mass of A.
So basically here we're defining the left part and the right, the left click and the right click to be 1 under A.
Yeah, like, everything else is just 0. Every other part, I have 0 weight of A. Yeah. When I omit writing, it means it's 0.
So it's just different functions A, right?
Yeah, different function A.
Yes, okay, so I just want to clarify this with respect, if you take it back to the star problem and the path problem
Yeah.
in the previous slide.
Yeah, the path, yeah.
So this can essentially be mapped to the star problem, but the path, because you have multiple A's over there, which is why we cannot, and if you cut through one, you still have two different sparse A's, which is why we cannot. So the path problem is a generalization of the star problem, right?
The path problem.
If you go to the previous page.
Yeah.
So every point on the path has some a equal to
Yeah, yeah.
1,
Every point here, like a is 1,
1,
2, 2, 2, 2,
okay,
2, 2,
yeah,
1.
okay,
Yeah.
yeah. So which is why we cannot say it's a generalization of the star problem,
Star.
because the star.
Okay,
you can,
I feel I need to finish soon, but we talking.
yeah, sure.
Yeah. So like, yeah, I'll. So I hope that at least today you at least get some intuition what do we mean by expanders? This is a notion we use throughout the course. Next time I will say that we can solve problems very quickly on expanders. But not all graphs are expander, and that's why we need expanded decomposition. So we see this next time.